Okay then, so we can start. We are still in probability basic. So you have done 2 classes on probability and statistics, mostly probability and distributions, but there is still something left. So I will try to cover that. It's statistical inference. And in particular, what is important for us is maximum likelihood estimate. But before going there, we should know a little bit about statistical basic ideas about sample mean, okay, sample variance, and things like that. Because this is exactly what you do in practice. Okay, in practice, you deal with samples. Real world data comes in samples. So that's why statistics plays a major role. And there are statistical estimates you are supposed to do. Okay, what is the average? What is the median? These are statistical terms. Okay, so real world essentially deals with statistics. So let us look into some statistical like motivation. So one of the very prominent one is politics, where statistics plays a role. If you look at the statistical data, you can have many types of statistical data based on demography, gender, okay, ethnicity, age, and so on. And statistical estimation usually would start with some samples, obviously. So you will go around and you may have some questionnaire, and you will have some questions related to gender, you can have some ethnicity, and so on. And then who is planning to vote for whom. So in this case, it's the US election, so it's Biden versus Trump. So these are the statistical data we have. So college graduates, like 55% prefer Biden, and then 42%, and so on. Okay, so and statistical estimation would mean that I go out in the field and through samples. In this case, sample consists of set of people, and I will say in this case exactly it's sample size 15. So there are 15,318. Okay, and we have quite a few things as well. So here we have shown error margin as well. Okay, so if you see error margin, these are the gray ones. It's hard to see. So sometimes in your estimate, you should kind of also show some amount of error margin. Okay, so if you go and build some more statistical idea, then you have ideas about confidence interval and things like that. Okay, so we will only do what is good for us for generative modeling. Okay, so as I said, you have error, but then what are the conclusions you can make? Will your inference fail? If it fails, how much? How confident you are of your estimates, and so on. Okay. Back in India, when I made these slides 2 years ago, then I teach some of these to UG students as well. And so back then we had elections going on in Bihar, and we had a big fight going on between NDA and Mahagathbandhan. So Mahagathbandhan is non-NDA allies. Okay, NDA is like BJP plus, and Mahagathbandhan is like Congress plus. Although in the state of Bihar, the local parties are more dominant, not necessarily Congress. So they unified, and then we have poll agencies. They go to the state, and then they do predictions, and then they say that these are the estimates for the non-NDA, and these are the estimates for the NDA, and then those who are not part of the alliance are the last 2 columns, and these are the projections. That's why they call this poll of polls. Is like you take polls and then you make a global poll of these. And if you see, then most predicted that Mahagathbandhan will win or acquire the majority. So in Indian parliament system, the majority means like you have to be more than the half to gain a majority. So almost everyone projected them to win. But then if you see the actual result, then NDA got 125, so they got the majority. So if you have data like this, then as a statistician, can you have some confidence interval or margin to say, okay, although you're predicting this, but do you have how much confidence you have in this data? Okay. So with this motivation, of course, there is a motivation behind generative AI, and and there we will talk about more about the data collected from images, from text, and then we would like to generate those data. Okay, so we will come to that more precisely, what exactly that means. So here in what we have done, we were doing statistical estimates about who is winning or who is losing, but generating an image is a little bit different. There you want to, of course they are related, but there you want to even know the generative process. You are learning the generative process. Okay. If I go out and collect certain data, the way I observe the data, okay, that's the process I'm observing. Okay. So in generative images, in generative modeling, you're trying to learn the process itself. Okay. See, if I'm picking out the pixels from an image, then certain occurrences of pixels, likelihood of certain occurrences of pixels in some way defines a cat. Okay, so it's like we are interested in the generative process itself rather than just getting an estimate of some data like average, mean, or something. So we are going more than the basic statistical estimates. So generative AI is a little bit harder than just showing some statistical estimates of some parameters. It's a lot more than that. I'm learning the whole generative process. Okay, so you will see that slowly. Okay. Okay, so before going there, let us build the fundamentals. Okay, so first we define what exactly is statistical inference. Okay, so statistical inference is a collection of methods that deal with drawing conclusions from data. It's very simple. Okay, I collect data and I draw inference from the data, conclusions from the data, and the data that we are collecting is has some random variations involved. Okay, it's not exactly precise. There is some randomness there. So hence, our modeling itself involves a random variable. Okay, so some knowledge of probability is used. We need to work with the real data, and distribution of the data obviously is not known. Okay, and statistical inference problem is to determine an unknown quantity to get some data and then estimate the required quantity using the data. So statistical inference means that someone is asking you to estimate something, okay, and you as a statistician will go out, collect the samples, and then do something on the samples and give an estimate of what is required. In the case of elections, you are estimating the who is going to win. Okay, Biden or Trump is going to win, but someone can ask something else other than those questions. Okay, so it depends what exactly you're supposed to answer. So in general, statistical inference problem as such is a very simple way to define. Now broadly, statistical inference is divided into two major classes. Okay, one is called frequentist inference or classical inference, and one is called Bayesian inference. Okay, so we'll try to get an idea about both. So in the frequentist inference, here the unknown quantity is assumed to be fixed quantity. Okay, we assume that it's not random. What we are going to estimate is not a random quantity, but the way we are going to estimate, we may be estimating that quantity via some random variable. Okay, so there is a slight difference. Okay, the quantity that we want to estimate is not random, but our approximator may be random. Okay, so it's assumed to be fixed quantity, not random. So the unknown quantity theta is estimated by the observed data. So let theta be the percentage of people who will vote for a given candidate. Then I can have an estimator theta hat, which is y divided by n. Y is the number of people among randomly chosen ones who will vote for the candidate. Okay, and so although theta is not random, we will estimate this via theta hat. So obviously y divided by n means that how many are going to vote for the candidate. So divide by n are the total number of people, and y is the total number of them going to vote for the candidate. So this will give you the percentage. Okay. So this is indeed an estimate because y depends on certain samples. You are not going to ask everyone if you're going to ask everyone, then it's no longer a statistical estimation problem. Okay, it's like you asked everyone, so you did the full election by yourself, right? So so here the challenge is that y is some random sample. So although theta is not random, we estimate it via theta hat, which is a random variable because the y itself is a random sample. The way I went out in the field and I choose this group or this group, that was my random choice, right? That creates the randomness, right? I could have taken first half of this and last half of that. So the fact that I'm choosing these samples randomly, that's the reason why our estimator is going to be random. So on the other hand, we have Bayesian inference. Here the unknown quantity theta hat is assumed to be a random variable itself. And furthermore, we assume some initial guess about the distribution of theta. Okay, so in short, Bayesian uses some prior. Okay, and the classical inference doesn't do that. Okay, so it means that, for example, the election in what happened in Bihar, you can think of what was the result 5 years ago. Can you use that? And of course, I'm not saying that you only rely on that, or let us say what happened in Telangana. So this year it changed. Okay, so could you have used the distribution from the previous year, the previous last election, and based on the current some sample data and the prior, could you have done a better prediction this time? Okay, so in nutshell, this is what Bayesian does. So Bayesian often is usually better if you have the prior, which is a good one. Okay, so let us see a small example. So consider a communication channel in which the information is transmitted in the form of bits. In each transmission, the transmitter sends 1 with probability p and sends a 0 with probability 1 minus p. So hence, if theta is the transmitted bit, then we can already assume a prior to be Bernoulli, okay, because it's transmission of bits. Okay, so with some probabilities like a coin toss. Okay, so we can assume that any experiment that involves 0, 1, heads, tail, only 2 outcomes are there. We can assume some Bernoulli, but obviously there will be it may not be a fair coin. Okay, it may not be a fair channel. So there may be a biasness of what is the probability that one bit will be transmitted and so on. So we can assume that there is a p which is not necessarily half. Okay, that's why we use generic p. Otherwise, you could have set p to be exactly half. So the fact that I know that it's a problem of transmission of bits, I can safely assume a prior to be Bernoulli. Okay, with p. So this is where I may go with the Bayesian inference, where I have certain ways of the prior, and then based on the current data, I will, with the help of the Bayes rule, I will update a new update my estimates based on the prior and the current sample. Okay, so we will see more concrete example later on. Don't worry if you don't understand it now. Okay, these are very high level stuff. Okay, so we will see some examples of how to do these things later on. Okay, so in statistical estimation, the first step itself is the samples. Okay, you want to estimate about something, the first step is to collect the sample. Now, you may, in fact, there are people who will work on just the sampling part. Okay, so it's like how to do sampling itself is a big thing. Okay, so should my sampling process have certain approach? Okay, so or should I always look for uniform sampling? Okay, so it depends. So so let us see one approach where we do it with replacement. So I choose a random sample of size n, x1 to xn, with replacement. So what does that mean? In a population, this is called population. So population is like everything. Okay, population is everything, and from population you pick sample. Okay, so this is what sample. Okay, so basically, if you want to see in terms of generative, you have collections of like cat images, and then from there your training data, you have some sample of these cat images, and you will, based on just those samples, you will learn how the pixels distribute themselves when it's cat image. Okay, So we will try to define what exactly is a random sample. Okay, so we will say that we pick x1, x2, xn. There are n sample size, and we will do it with replacement. The reason why we do it with replacement is we want to make it independently and identically distributed. Okay. So we choose a person uniformly at random from the population and let x1 be the height of that person. Let us say we are setting the height. Hence, every person in the population has the same chance of being chosen. Okay. The fact that we are doing it with replacement, then we are not really changing the distribution that much. Okay. That's the idea. So to determine the value of x2, again we choose a person uniformly at random and let x2 be the height of that person. Again, every person in the population has the same choice of being chosen. So you may say that you do the replacement, right? So what is the guarantee that I will not pick the same person again? It may happen. I'm not saying that it won't happen. Okay. It may happen that all these guys that I picked, since I'm doing it with replacement, I pick the same guy. Okay. It can happen in the worst case, but that usually don't happen. Okay. That usually it's very rare that all the person I pick, because I'm picking and then I'm putting it back, and I don't know where that guy went. I will again pick randomly from there. So obviously I don't know which one I'm going to pick, but I'm replacing. So there is a chance that I will pick the same guy again and again. But in general, in a very large data setting, it doesn't happen. Okay, because if you pick the same guy again, you will not get the true picture of the true or like some very good estimate of the population. So obviously picking the same guy again is a bad idea, obviously, but chances of that happening is very rare. Okay, so this is what we are going to do, and so basically we will pick one guy and we will assume as if that person is sent back, and then we pick another one, and then and so on, and then we will have this sample, okay, of size n. Okay, so and from this sample, since it's about a height, right? So from this sample we may estimate the average height of the population from just this sample. Okay, that is what real life is. Okay, real life you cannot do precise computations. Okay, even if you go to physicist or something like that, even they are approximating in many ways. Okay, so real life is very complicated. You are only dealing with some observations and you are predicting based on that. So here you will predict the average height of the population by just looking at the average height of the sample or any other data. Median, you will approximate the median from this sample. Okay, so that's what we do in practice, and later on when we do generative modeling, the training data will be some collection of cat images. We will not be getting all possible cat images. All possible cat images will be almost close to infinity, so that's not possible. So this will be our training data. Okay, and based on that we will learn a distribution, and that distribution, if we sample, then it will look like the image that we wanted to generate. Okay, so we work with random samples. Okay, and we used with replacement because it will ensure that xi's are independent and identically distributed. Okay, so this process that I do it with replacement essentially guarantees that these random variables xi's are independent and identically distributed. So if you remember independent, then joint probability will be product of the individual PMF. Okay, so that simplifies. Okay, we will see this in maximum likelihood estimate that we will do. All this simplifies. Okay, so ideally you should not have done replacement. Okay, ideally, because if I ask someone whom you are going to vote, and I'm sending that guy back again, and I might pull the same guy again, so ideally I should not have done that. But from maths point of view, from reasoning point of view, and it's very rare that I will pull the same guy again. So all this makes sense that I keep things independent, identically distributed. It makes the maths very tractable. Okay, so you will see this IIT everywhere. Okay, so we will have random samples. So far we are considering uniform. Again, as I said, even sampling itself could be done in many ways. We are sticking with the basic sampling, uniform sampling with replacement. Okay. So that's our sampling process, and this is the formal definition of a random sample now. So a collection of random variable x1 to xn, and this could be the height. So we know that random variable x1 could be some height h1. So it could be 150 centimeter, it could be 170 centimeter, something like that. So the random variables take the actual value and the probability is between 0 and 1. So, okay, so I may ask probability of x1 being equal to 170, something like that. Okay, so random variables just are a notation, just like in your computer program you have variables to denote some quantities. So here x1, x2, xn are just like variables in your C program where it encodes the numerical values of your problem. So in this case it's height. Okay, so nothing to be scared of random variable. It's just a placeholder for the numerical data. Okay, so so these guys are just the collected data, and they are random sample of size. If so when we say random sample, IID is implicitly included in our definition. Okay, so I will not say it's a random sample with IID. No, it's part of the definition. I say it's a random sample because it's independent and identically distributed. So I'm not going to say it again and again. Random sample means sample size and IID. Okay, so what does IID incur? So if there are a bunch of random variables and they are independent and identically distributed, obviously they have the same, they come from the same distribution because they are identically distributed. Identically distributed exactly means they are coming from the same distribution. They are random variables from the same distribution. Okay, so so obviously their CDF will be equal. So capital F notation stands for the CDF. So CDF corresponding to the random variable x1, and cumulative up to the current value x will be same as the CDF of x2, cumulative up to x, and so on. So CDF is same, PDF is same, obviously mean is same, variance is same. So IID implies so many things. Okay, so this is something you have to remember. Okay, IID implies all of these things. Now I can define a sample mean. So this is our first statistical estimate. Okay, the first statistical quantity that I want to estimate is mean from random sample. So I went out in the field, I collected data. That is my random sample. From random sample, what are the statistical things I can do? Mean. Let us calculate mean. Okay, so x1 to xn is my data, and it's a random sample. So all this quantity hold, like CDF are equal, expectation is same, and all this. So that's exactly what I said. And sample mean is defined to be like this. Okay, so sample mean is just the mean of your samples. Okay, so in my sample I had x1, x2, xn. I took an average of this usual arithmetic mean of that. Okay, arithmetic mean is the sample mean. Okay, and it turns out these are the only things you can do in general when you have random sample involved. The average of the population you will estimate by average of the sample of the random sample itself. Okay, so what are the properties of sample mean? Okay, so we can write down the properties of the sample mean. So it turns out the way sample mean is it's the usual average. Then the expectation of the sample mean is actually the true mean, and we can do this very easily, right? If you go here, you do the expectation of this, right? We want to compute what is the expectation of x bar, right? So expectation of x bar is expectation of this guy, and expectation is linear. So since expectation is linear, it will be sum of the expectation of all this, and xi's are IID, so each of them are equal. Okay, so there are n of these same quantities, and n gets cancelled, and each of them has expectation mu. So this is like n times mu on the numerator divided by n, so you get the n. N gets cancelled, so you get the mu. Okay, so it's very easy exercise. Use the linearity of the expectation to show that expectation of the sample mean is actually the true mean. Okay, and variance of the sample mean is not exactly the true variance, but it is scaled by n. So it's a slight change now, right now. Okay, so it's divided by n. So this also you can verify. So compute the variance, right? So what is the variance of this? Right. So how does variance applies to the sum of the random variable, right? So do you remember any formula for the sum when a variance is applied on the sum? So if I have variance of ax plus y, so how does it split, right? And this is how much? A square variance of x and y you assume to be constant, I guess. Okay, so let us put it constant. But what if I have two random variables, right? And these x and y are random variables, and their ID, well, how does it split? Just splits, right? So this is variance of x plus variance of y. So basically we want to combine both, and that gives me, so 1 by n is like a, and in place of b I have this x2 plus x3, so we apply recursively, so it will be 1 over n square and variance of x1 plus x2 and so on. So variance of x bar is 1 over n square, and this is variance of x1 plus x2 and xi is being ID, all the variances are the same. So let us say that is sigma square. So there are n sigma square by n square, and n gets cancelled, so this sigma square by n. Okay, so these are simple things. We have sigma square by n. So variance of a sample mean is not necessarily the original variance, but it's scaled by n. Okay, and weak law of large numbers. Actually, weak law of large numbers is defined to be like that. Okay, so weak law of large numbers says that if you take a bunch of random variables, add them, if they are IID, if you add them, then the probability of them being different from the true mean, okay, being greater than epsilon. This is actually for all epsilon. So basically epsilon could be very close to 0. So probability of the sample mean, where n is in part of x bar, obviously, because x bar is sum of these x1, x2 plus xn. So obviously n going to infinity means your sample size is going bigger. You are computing the sample mean over bigger and bigger sample size. So if you do that, then you are pretty much as n tends to infinity, then the probability of the sample mean being far away from the true mean is very less. Okay, so it makes sense if in this class, as myself I am taking only 2 guys, then if I compute the average, then this estimate is much worse than I am taking the whole of this. So my estimate is improving, obviously. Okay, n tends to infinity exactly means that I'm covering the whole population. So obvious, this is very obvious that that my sample mean will approach the true mean, obviously. Okay, so no surprise. Okay, this is also interesting. It's called central limit theorem. It's interesting because this gives me a way to always transform my problem to a normal distribution. Okay, this is why you see normal distribution plays a central role in data science, because regardless of whatever distribution it was, if it's a big data problem, then it can be approximated very well by normal distribution. And this is what central limit theorem says. Now let us look into this, the claim that I made, why it's true. Okay, so let us see this. X bar is your sample mean, and x bar is a sample mean of a distribution that is not necessarily a normal distribution. Anything. Okay, so this x bar could be Bernoulli, it could be binomial, it could be Poisson, it could be geometric. Okay, there are hundreds of distributions. So what is interesting is that if I make a sample mean, okay, for example, the height of students in this class may follow some distribution which is not necessarily normal, but what this is saying is that you collect the sample, you compute the sample mean x bar, and you scale it. You do the additive scaling, so it's like you subtract by the mean, and you divide by sigma divided by square root of n, and n is the sample size, obviously. So so if you scale it in this way, exactly this way, okay, which means that you will do like this, then this starts behaving like normal distribution. Although x bar that I computed was not necessarily from normal, it came from some other distribution. Okay, Bernoulli, whatever. Okay, so that is important, but there is a caveat. There's a caveat that it will start behaving like normal when it's a sufficiently big size problem or big data problem. That's why in generative modeling, whatever, we are always dealing with training data which is very big. Okay, 10,000 is also considered big. Okay, 10,000, 20,000 MNIST or ImageNet or all this data, these are considerably big. So all this makes sense because mathematically it should be n tends to infinity, but I'm okay if it's also approximately equal to phi x. If you have recalled, I don't know if this notation was introduced to you, but phi x is a pretty standard notation for normal distribution CDF. Okay, so phi x is a very standard notation, is a CDF of standard normal, not normal, standard normal, mean 0, variance 1. That's called standard normal. Okay, so of standard normal. Okay, so whenever you see phi x, it's actually CDF of standard normal distribution. Standard normal distribution is a normal distribution with mean 0 and variance 1. Okay, now why is this interesting? So what, right? If I do the scaling and all this behaves like, so if I have to compute the probability of Zn being less than x, then it could be computed via phi x. How many of you have looked at phi x values? Did you encounter phi x values in some computation before? What type of values are phi x? Is PDF of standard normal integrable function in closed form? No. Do you agree with that? Okay, you can have a look. Okay, it is not necessarily integrable in the closed form. Okay, so hence there are only numerical values. So when you are actually working with these phi functions, you will be given tables. You will be given table of data. So someone will tell you compute phi of x, where x is some numeric data 0.3 or whatever, and then you will go and look at the table. This table itself won't be precise because x is a continuous variable. So your data could be given to be phi of tabular data will be there, and it will be like 0.3, 0.4, something like that. It depends on the table how precisely the table is made. But if someone is asking you, go and give me the value of phi of 4.3, then maybe you will report this 0.4 value, okay, as an approximation. Okay, so although the data, although the real world data we are dealing with may not necessarily be normal in the small sample size, but as the sample size grows, they start behaving like normal. So it's not just. So what I'm trying to say is, it's not just for computation point of view, but it's also an observation. As you go to bigger data, things start behaving like standard normal. Okay, so you take bunch of Bernoulli random variables, you add them, and then look at those. It will start behaving like bell curve. Okay, so this is our standard normal. So that makes sense. Okay, why it makes sense, right? Why things start behaving like standard normal or normal? Okay, as soon as your data size starts increasing, right? It makes sense because things that are common will be a lot more than the rare things. It's a fundamental thing, right? Rare things are rare because they are less in number. So it's very natural that in a big data environment, number of people who are very short will be very small. Number of people who are very big, very tall are very small. Most people are concentrated around average. This is a very basic feature. Okay, so it's no surprise that most data will start behaving like this. Okay, so it's okay to think of this as it is okay to even start with standard normal. Okay, as a model. Okay, so we will see this. We will be doing a lot of standard normal at some point because of all this. Okay, because it's good enough. Okay, so this is what central limit theorem says, that regardless of the distribution you have, as your sample size grows, if you do a proper scaling and both additive scaling and multiplicative scaling, then the PDF or the CDF in this case of this scaled random variable Zn is behaving like standard normal. I can use this in calculations. Okay, someone might give me a problem like this with data like this. I can use this as an approach, numerical method, to actually find these values. So I will given a sample, I will do the sample thing and then do the scaling and go and look at the values. So you may have asked this this original question of give me the probability that that Zn is less than or equal to x, but then this could be transformed into this, because Zn could be substituted like this. So in place of Zn I can substitute like this, and then I can give you some estimates. So then I can play around with the inequalities, okay, and adjust with whatever you are asking me to do in the inequalities. So from there I can give you results on x bar. Okay, so I can use this in actual computations, okay, later on if I need so, okay, because my original problem will be based on some sample mean maybe, okay. So I'll just substitute everything there, okay, and then so the yeah, whatever question you have, you have to transform in this form, and then read out the table values, and then kind of whatever question was originally asked in x bar, you can answer by just reverse engineering this. Okay, so maybe I can do some examples at some point on this. Okay, how this is a big deal. Okay, so how central limit theorem could be used in estimations. I will do some examples, concrete examples later on. Yeah, if you do this scaling, then it does become standard normal because you have subtracted the mean. Okay, originally it may not have mean at 0. Okay, the fact that you have done this additive scaling, it shifts the mean to 0. If you don't do that, then it will have shifted mean. Okay, so your original distribution mean was mu, right? And I want to go to standard normal with 0 mean. So the very fact that I have subtracted it, it will normalize to 0. Okay, and actually we can prove these things if required. And the very fact that I divided by sigma by square root of n, it normalizes the variance to be 1. Okay, so we can concretely prove that. Okay, and it will be like this, as I said, right? Because there will be more students with average height, close to average height. There will be a lot more students with average height than students with very small height or very large height. So that's like the intuition behind that. And not just about height, anything you think about, it is like this. Rare things are rare, that's why we call it rare. There, if nothing is rare, then it's not even a kind of distribution, like everything has the same probability anyway, right? So that's a basic intuition, like, okay, so normal distribution are pretty like intuitive. Rare things happen in the very fact that they are rare, it happens less in number, hence you have the tails. Okay, and frequently things are just around the mean. So yeah, that makes sense. So we might use this in calculations. When we will do calculations, you will see how, given original problem, I go back to there and then solve my original problem by using this central limit theorem. But right now there is something called order statistics. I may not need it immediately. I've read some papers on generative modeling where they use that. So in the passing, I'm just going through this. Even if you don't remember and everything, we will recall it again, everything, okay, whatever is needed. This is just a way for you to kind of revise a little bit. But so there is something called order statistics where there is some ordering of the random variables involved. Okay, there are certain cases where we have ordering that x1 necessarily is always smaller than x2, x2 is necessarily smaller than x3 and xn. I mean, the way it's defined is like that. X1 is the minimum of all, and hence I get a new random variable x parenthesis 1, and this is the second largest, and so on. So in those cases, this is called order statistics because there is ordering involved, and then we can write down the CDF and PDF. I won't spend too much time here. When it's needed, I will come back to that. So this is order statistics, and PDF and CDFs are can be explicitly written in this way. Okay. So that's how order statistics could be defined. I will skip this for the moment. Okay. So what we have seen is that given a population, I take a sample, and from sample I want to learn the estimates for the statistical data, statistical quantities. Like so far we have seen mean, and mean we estimate by sample mean. Now we can kind of generalize this estimator. So for mean we define sample mean, but we can say that let us define a generic estimator, not just the arithmetic mean, but what if there is some estimator H, okay, that takes in these n samples and then it gives me some estimate, okay, over that. So for example, if it's sample mean, then our H function is the arithmetic mean, okay. So we can just like write things in a more generic way. Now when we define an estimate, then we have a concept of bias, how much bias my estimator has, okay. So if I am defining sample mean, then what is the bias in my approximation? So the bias is defined like this. So bias of the estimator theta hat is expectation of the theta hat minus the actual theta. So if bias is close to 0, then theta hat is closer to theta, obviously. So in that case, our estimator is doing a pretty good job. It has 0 bias, okay. And we said that theta hat is an unbiased estimator for parameter theta if the bias is equal to 0. So let us calculate the bias of the sample mean. So if I calculate the bias of the theta hat, then by the definition, expectation of theta hat minus theta. So expectation of theta hat, I apply expectation here. So this is n of these xi's divided by n gets cancelled. So you have expectation of xi minus theta, but expectation of each of the xi was theta. So it's 0, okay. So sample mean is an unbiased estimator. Sample mean is an unbiased estimator of the true mean, okay. Sometimes you may have an estimator which has some bias, okay. So in this case it's not. Now just that your estimator is unbiased does not necessarily mean it's a good estimator. Why? Okay, because things can go wrong. Let us say that your estimator just takes the x1, okay. Your estimator is just x1, and then theta hat 1 will also be an unbiased estimator, okay, because expectation of theta hat 1 minus theta hat 1 was x1, so it's x1, so expectation of x1 was also theta. So theta minus theta is 0. So what is wrong here? What is not wrong, but what is bad here? What is bad here is that I could give an estimate of the mean, but just looking at one sample, right? That's bad, right? How could it be like that? It's like saying that I've just picked one guy from here and took his height, and I'm telling you that this is the average height of the class. That's not a good idea, right? But it looks like it's an according to this, it is a unbiased estimator because my bias is 0. Okay. So you see what is going on here. What is going on here? There is a little bit of a mismatch. The way I interpret this is that not necessarily one guy is a true representative of the whole distribution, right? Obviously, right? So from maths tells me that each of the xi's are coming from the same distribution. So I pick one guy and I compute the expectation for that, and that is good enough. So maths tells something else. Reality will tell you something else. Okay, reality means that I should have good handful of data in hand to compute the good average of height. Okay, so just because your estimator is unbiased does not necessarily mean, because unbiasedness is a theoretical concept with IID and all this, things are making, so because of this guy being IID, the expectation of x1 matches with the true expectation, right? That's what IID means. So we use IID to make our lives easier, for easier calculations we will also see later, but you can fool around like this, okay? Because in reality we do know that just taking one or two guys and computing average is not a good idea, okay? So maths assumptions and what do you do in practice? Okay, so maths may tell you that, of course, another way to look at this is that even the measure that we use, the biasness, needs to be updated. Okay, so we need another parameter, another measure to define our estimator. So that's why we will go for mean squared error. Okay, the mean squared error will prevent such issues we will see. So in some cases you may be okay with computing bias and you may be happy, but it's a bit risky. Sometimes you may also want to go for mean squared error. That will kind of prevent you. So mean square error is like this: expectation of theta hat minus theta squared. Okay. So now you compute. So earlier what you did is the bias of this, where you just picked one guy and computed the average, and bias of this, both were 0. But now it won't be. Okay. So now biasness or the error of theta hat 1, which I am claiming here, is larger than the error of theta 2. So meaning, computing average from a bunch of sample gives me lesser error. Lesser is better. Okay. So MSE lesser is better. Okay. So the MSE seems to be a better measure of the quality of your estimator. Okay. But again, you can keep building on this. Okay. Even MSE may not be the best. Okay. So it depends how far you want to go. But yeah. So MSE is better, and I believe I did the calculation. So you can go through this very quickly. Simple tricks are used. Basically, you just go through the process. So compute MSE theta hat 1. So by definition, MSE theta hat 1 is expectation of theta hat 1 minus theta whole square, and this will be, since theta hat 1 by our assumption was x1. So we substitute that x1 in place of theta hat 1 minus this is theta was expectation x1 is IID. So I can just replace that here, and this is nothing but the variance of x1. This is how variance is defined: expectation x1 minus expectation of x whole square. So this is sigma square. Okay, and then we go ahead and compute theta hat 2. MSE theta hat 2 is by definition theta hat 2 minus theta whole square, and theta hat 2 by definition was sample mean minus theta whole square, and this turns out to be variance of, if we expand this, then this will be variance of x bar minus theta plus expectation of x bar minus theta whole squared. Yeah, there is a difference. You see, this square is inside, and this square is outside. Okay, so if you expand this and apply do the algebraic manipulations, I leave this up to you. It will simplify to this. Okay, and so basically I have also given the hint here. So last equality should be equality, I guess. It follows from expectation of y square is variance of y plus expectation of y whole square. In fact, we applied this directly here. You got that, right? In fact, this was just in place of y, I see x bar minus theta. Is that okay? So in place of y, so this like whole thing is like y. So just apply this. So this is like expectation of y square is variance of y. So the x bar minus theta was our y plus expectation of x bar minus theta was our y. So this is like this. So expectation of y whole square. So we just apply that formula here. And what we also note is that variance doesn't change with additive scaling. So variance of x bar minus theta just boils down to variance of x bar, and since theta is a constant, and also expectation of x bar minus theta is 0. We know that, right? Expectation of the sample mean was true mean, right? So that's also easy because you see this is expectation is linear, right? So expectation of x bar is theta, and expectation of a constant is the constant itself. So it's like theta minus theta. So that's 0. So this term goes to 0. So basically we have variance of x bar left. So everything now boils down to variance of x bar, and we have calculated before the variance of x bar is theta sigma square by n, right? Now you compare, right? So MSE theta hat 1 is sigma square, whereas MSE theta hat 2 is sigma square by n. For n greater than 1, indeed MSE theta hat 2 is lower. Okay, the error is lower as your sample size is growing. So your estimator error is lower, okay, compared to the one where you had just one in the sample. Okay, so MSE is a better estimator. Okay, so okay, so that's also a small relationship between MSE, variance, and bias. Okay, so it's very simple. You can have a look at this. It's just expansion of this. And we can also define something to be consistent estimator. So if I have a bunch of estimators like theta 1, theta 2, theta n be a sequence of estimator, then we can define something called consistent estimator of theta. When this happens, so basically I am building a sequence of estimators. So if it so happens that n tends to infinity, then theta hat n minus theta gets closer basically. So if it happens in the limit, then we say it's a consistent estimator. And there is a theorem where I can also say that this theta hat n are consistent estimator if the MSE goes to 0. Okay, so there is a proof of that as well. It's very simple. You use Markov inequality, and so you can have a look at this. Okay, we just need to know the results rather than the proof, but sometimes looking at the proof you know more. Okay, so but we don't want to go too much into the proof, we just want to use these results. Okay, now so far what we did is sample mean. So computing the average, okay, that itself is a big deal. So we could do sample mean. We saw about biasness in our approach, okay, but the biasness can be tricky, so we went to the mean squared error. Okay, mean square error is usually lower than the as the sample size grows, mean square error in fact can go to 0. Okay, so because it's divided by n there. Okay, so what about variance, right? So we have these statistical terms like mean, so we dealt with that. Now what about variance? And we have to do it with samples. Okay, so of course we can again define variance from the samples. So we can define variance to be like this. Okay, you can say that why it's n minus 1. There is a trick there. It's just that with n minus 1 rather than n, it becomes an unbiased estimator. If you put n, then it is not exactly unbiased. Okay, with this small trick where you just have n minus 1 rather than n, it becomes so you can prove that the bias of this sample variance is 0. Okay, with this n minus 1. So that's very interesting. You can see this. So for us, it's enough to know that given a sample, I can compute the variance or not. Yes, so I can compute variance like this. How can I compute this? Well, all these xi's are known to you. So again, these are the heights of n students. So I have exact data with me, k1 to n. I have computed the sample mean so I know the average of the sample mean, and I know the individual values. I subtract n times of that. So I indeed, given a sample, I can compute the sample variance. And standard deviation, usually you take the square root of the variance. Here also you can take square root of the sample variance. Okay. So this is a small exercise to compute the sample mean and sample variance. So you can have a look at this later. Okay, so this is a motivation for the maximum likelihood. In fact, this is directly related to what we are supposed to do. So let us go through this. Okay, this is the one that will relate pretty much, okay, to generative modeling, especially for images. Okay, so let us see this now. As I said, we can estimate mean, we can estimate variance, whatever. Okay, but what about estimating the distribution itself? I want to know the distribution that produced that result. Okay, so let us play with some experiment and try to estimate the distribution itself that produces that behavior. Okay, so let us play with some experiment. So I have a bag that contains 3 balls. Each bag is red or blue. Each ball is red or blue. So this bag contains red or blue balls. Obviously, I don't know how many of the red and how many of the blue are there. So let us call the number of blue balls to be theta. So what are the possibilities for theta, right? So blue balls could be 0, could be 1, could be 2, or could be 3, because there are total 3 balls. So there may not be blue ball at all. There may be 1, 2, or 3. I am allowed to choose 4 balls at random from the bag with replacement. Obviously there are 3 balls, but then I can choose 4 balls because it's replacement. Okay, so I pick one and put it back, and then I pick another one, put it back. So this is the sampling process. Okay, I have a bag with red and blue balls, and I will pick 4 samples. Okay, x1, x2, x3, x4. Okay, so and then so since this is about red and blue, this variable will take binary values. So we may say that it's 1 if the ith chosen ball is blue, and we may say it's 0 if the ith chosen ball is red, right? So we can go with an intuitive template because someone already told me that it's it could be either red or blue. So when someone tells me like that, then I have some idea that okay, I'm going to choose Bernoulli. Okay, because Bernoulli is like that, blue or not blue. Okay, something like that. Okay, so that gives me an intuition to say that okay, let me go with Bernoulli as a template distribution. Okay, just like you do line fitting. Okay, just like you do curve fitting for the data. Here you want to do distribution fitting for the data. Okay, so distribution is your parametric distribution. Theta is your parameter. Distributions, just like your neural networks, just like your curves, line fitting, they have parameters, weights. Similarly, here we have distributions with weights. Weights are the parameters of the distribution. In this case, it's theta. Okay, so I take it as theta by 3. Okay, even if I don't do divide by 3, I believe it will work. Okay, but my guess is like there are 3 balls, so I want to go with theta by 3. Okay, but from data theta will be learned anyway. Okay, so I don't think that's the critical thing. Okay, so you can go with the assumptions that your random variables xi are going to behave like Bernoulli theta over 3. Okay, obviously theta is not known, but what is known is the samples that you have. This is your data. You are allowed to collect the data, and based on the data you are supposed to identify this theta. This is called probability distribution fitting. Okay, and so let us do sampling. So we do sampling. Okay, so sampling here means picking a ball and saying whether it was so theta corresponds to blue ball. Okay, so xi1 if the ith chosen ball is blue. Okay, so basically it's 1 if it's blue, otherwise 0. Okay, so I picked a ball, the first step, and I found it to be a blue ball. Okay, and hence I put a 1. I got a 0, so the next ball that I picked was a red ball. The third ball I picked was a blue ball. Fourth ball I picked was a red ball. Blue ball. Okay, so blue, red, blue, blue. This is the data I collected out in the field. This is my sample. Okay, this is my sample. Sample size is 4. Just based on this 4 sample, I am going to predict the behavior. What is the behavior here? It's like something is there in the nature, and it's doing something in an interesting way. Okay, if I go and look at nature, something is happening in certain way. Okay, so this bag is like that. Bag has certain mystery, but when I look at the bag and when I pull something from the bag, it's behaving a certain way, and there is a behavior. What is the behavior? Behavior is that it's giving you more of the blue balls than the red ball. That's how it's distributed. That's what distribution means, right? How things are distributed. So it's like the distribution has more of the blue balls. Now can you build a distribution that behaves like that? Because if I sample from the distribution, it should start behaving like that. It's exactly the same problem as saying that I trained on 4 cat images and I build a distribution. From the distribution, if I sample, it will start behaving like cat. It will start looking like cat. No big deal. This is exactly what is the fundamental statistics or probability idea involved, but things are not easy because you can already think what could be the complexity if I do it into 4 images. What are the problems with images? Think step by step. Dimension, pixel values. If it's a color image, there are 3 channels, maybe 4. You include the intensity and so on. So red, blue, green. Each pixel value takes value in 0 and 256. There is a lot more going on in images, right? So that's where approximations will help. That's where some amount of maths will help, because you have to approximate there for sure. Okay, but at the fundamental level, this is exactly what you will do. You will be fitting probability distribution for pixels. It's just that they are a lot more complicated. Okay, this x that I'm picking here for an image is not just one value. It's like red, green, blue channels. Each have pixels can take 0 to 256. See the complexity? There is 64 by 64 just for one channel, 64 by 64. 64 by 64. Okay, pixel, probability of picking 1 pixel, that corresponds to this. That gives me one RGB value, gives me one color, and that each of them varies 256, 256. Okay, 256 cube possibilities are there. Okay, just for 1 pixel. Okay, so it's like picking these pixels from the bag. You have a bag of these pixel values, and in your training data you will have a lot of these. Okay, now based on this, let us say, as I said, in a big data environment where there is a lot of pixels, it's very high. So I will go with let's say normal distribution. Okay, in the end, like a very large setting, normal distribution approximates quite well. So I may go with normal distribution, maybe high dimensional normal distribution. Okay, but the complexity is way higher here. Okay, so you can just keep this as a reference. In fact, we will come to that in 2-3 classes. We will start with a basic approach and we will see where we get stuck and how we improve. But now let us come back and see, even for this simple problem, what does it mean to fit a distribution, right? I have not told you how to fit a distribution yet. Even to solve this problem, what are the steps I'm going to do? So I got the data. And I have gone with it just like fitting, right? You have some inductive bias. In any machine learning setting, you always come up with some inductive bias. What is inductive bias? Inductive bias is the model that you want to fit, okay? If it's a image vision problem, you will go with CNN type networks, okay? If it's text, then you go with RNN type network. These are called inductive bias. These are the these are the set of architectures functions that you think that it's going to do well, okay? So here we are coming with our inductive bias that Bernoulli is going to do a good job here. So we go with this parametric distribution. You could have gone with any other also. That's what I'm saying. Okay, what you go with is your choice. Which neural network you choose for your data, it's your choice. Okay, so there's no hard written rule. Okay, but there are like intuitions. Okay, something works better than other. Okay, so in this case, this is our parametric distribution. Now we have the data. Okay, and what are we going to do? These are the steps we are going to do. So find the probability of the observed samples, this for each possible theta, and find the values of theta that maximizes the probability of the observed sample. Okay, so basically it will boil down to an optimization problem where we have to find a theta that maximizes the probability according to the data we have. So let us try to have this. So for according to our assumption, xi follows Bernoulli theta over 3. That's the template I went with, and the PMF values for that, how will because it's Bernoulli theta over 3. So if it is 1, then it's theta over 3. That's how Bernoulli is, p or 1 minus p, right? So in this case, our p was theta over 3. So if x is 1, if it's heads, then it's p. If it's tails, it's 1 minus p. That's how you might have learned in the previous class. So in our case, if it's 1, it's theta over 3. If it's 0, it's 1 minus theta over 3. So this is our PMF, okay, probability mass function. So these are probability values. Now since xi's are independent, that's where it helps, okay? We always assume independent and negligent because it simplifies the joint distribution. As such, joint distributions could be very complicated, but if it's independent, it's very simplified. The joint PMF is product of the individual PMF. That simplifies our life quite a lot. So in our case, what we have observed from the data, it's 1, 0, 1, 1. So we put those values there, okay? So first one was 1. Okay, so since x was 1, the PMF value was theta over 3. That's fine. The second observation was 0. Okay, so for 0, our PMF value was 1 minus theta over 3. So that's our second one. We are reading out from here. Okay, so now what about px3? So px3, the third one was 1, so it's theta over 3, and then the fourth one was also 1, so that probability value was again theta over 3. So this is the joint PDF we have. Okay, and this is the function in theta that we have. Now all you are supposed to do is to maximize the probability, right? So which values of theta gives you this highest value of the probability, because that's what you want to do anyway. Like what could be the best fit for your theta? Okay, so you because it's a probability, right? So probability higher is better. Okay, you want your data to give you the highest probability. Okay, so that's why you will maximize rather than minimize. If you build a loss function, then minimizing makes sense. Here it's maximum likelihood. These are, so you want to maximize the likelihood of your probability. So that's why it's maximizing this value for theta is the optimization problem. So now it's an optimization problem. It's a very simple looking function, at least to me. So how do you maximize a function, right? So it's a simple optimization problem. Maximize f of theta, where f is this, right? So to maximize, the usual basic thing is check where the gradient is 0. Well, there is a subtle thing that just gradient being 0 is not enough, right? Because gradient 0, but gradient is also 0 here, right? So you can be in a trouble that gradient being 0, you might have reported a minima rather than maxima. So you need to make sure that places where it's 0 is the one where it's maxima, okay? If it's countable, if there are finitely many theta for which this is 0, you can individually check each of these and see that it was indeed the maxima and report that theta. That theta is the theta for which the probability distribution fits the data, okay? So in our case, theta, yeah, exactly. So actually it's the discrete value, right? The way we define theta to be is like this, right? It's a discrete value, right? Okay. So since it's a discrete value, it could be 0, 1, 2, 3, and so on. So yeah. So then it makes sense that I just check for only these values, and then the one for which it's And here also I am a bit, because it should be the maximum value, but then I think it's 0 here, sorry, okay. I think I may have done some mistake. It is, I believe, 0.0247, and this is the highest one because it's 0.09. So we report, and for theta equals to 0, the probability is 0 because, why? Theta 0, because the data didn't tell you, right? Because theta 0 means what? There were no blue balls, but we didn't see that in the data, right? So it's a good that we are getting 0 because it was not the case. We did get a red ball at some point. So it's not that I mean theta was blue ball, sorry. So being 0 ball, probability being 0 ball is not correct because we did get, in fact we got 3 blue balls, and it's also not true that we got 0 red ball, all the blue balls. That's also not correct. Theta equals to 3 means all the 3 were blue balls. That's not correct because the second one was red one. So that makes sense that theta 0 and theta 3 was 0, and then it's about which one is max. So here 0 is missing, so theta equals to 2 is a good estimate here, okay. So so hence we choose theta hat, which is the estimator. When it's estimator we call it hat, okay, theta hat equals to 2 as our estimate for theta. So so this process, this observation with a bag and blue and red balls, the way it is distributed, it behaves like Bernoulli 2/3. Okay. So what this means now is that this can simulate what was in the bag. That's what we want to do as a generative modeling, right? Now I can sample from here. Okay. I can sample from this distribution, and it will behave like the bag with this red rules. And this is exactly what you want to do with the images also. Okay, you want to fetch some kind of a distribution, and then once the distribution is learned, when you sample, it should start behaving like what it was trained on. Okay, which in this case could be the cat images, right? So the bag, for generative modeling, the bag consists of cat images. Okay, it's just that it's way too complicated. Okay, in fact half of the course is just about that. Images and videos, first half. Second half is mostly on the text and so many things. So that's what we are going to deal with in a lot more detail. So what we understood is we build this kind of intuition at the first step that that we can have some template distributions. We may start fitting the template distribution based on the data. So this gives us a very generic way to formulate something called likelihood and log likelihood. So as you have seen, we had samples. In previous case we had 4 samples, so we can talk about n samples, and then we can build this joint probability distribution with some parameter theta. Okay, this theta does not have to be one parameter. So which distribution has 2 parameters? Gaussian. Okay, so Gaussian has 2 parameters, mu and sigma, or sigma square variance. So some distribution have 1, some distribution have 2. You can mix distributions as well to have many parameters. Okay, so we can build on that. Okay, so in general, when you see theta here, it does not have to be one scalar theta value. It could be a vector of theta. Okay, so we are writing this in a very generic probability distribution function. Okay, now which one you pick and all this depends on the problem at hand. So we can build a likelihood function. Likelihood function is nothing but the joint probability distribution with the parameter theta for the distribution. And if it is a discrete, then we have the PMF, and if it's continuous, then we have PDF. Okay, so there's a slight notation change, P to F. Okay, so this is the standard notation that we try to use. And there are cases where rather than looking at the likelihood, you may want to look at the log likelihood because it simplifies, especially if you look into which one, Gaussian, even other. Okay, so but if you look at the Gaussian, you have the exponential something, right? If you take the log, the exponential goes away. It simplifies a little bit. Okay, so there are cases where so maximizing likelihood or log likelihood, you have to be a bit careful that it should be equivalent, right? So you are saying that no, I'm not going to use the likelihood, I'm going to use the log likelihood and rather maximize that. But you have to be a bit careful that the maximum of this corresponds to the maximum of this. Okay, so some care is needed because I'm not working with the actual likelihood, I'm working with the log likelihood. The theta for which this got maximized should correspond to the same theta where that got maximized, right? So that's called log likelihood. And you may write down likelihood function for binomial and exponential as an exercise, and anyway I will discuss this in a little bit more detail in the next class. Okay, but for today's class we can stop. Okay, so thank you.